So in yesterday's class, we discussed about the displacement as a function of time, velocity as a function of time, and acceleration also as a function of time, right? So what was it? If you write in terms of y, it is a sine omega t plus phi naught. If you write velocity as a function of time, it will be omega into a into cos of omega t plus phi naught. If you write acceleration in terms of time, it will be minus omega square a sine of omega t plus phi naught. Similarly, if you write the displacement in terms of x, it is a cos omega t of omega t plus phi naught. V of t is minus a omega sine of omega t plus phi naught. Then acceleration as a function of time will be minus omega square a cos of omega t plus phi naught. Omega t plus phi naught, right? So these are all the expressions that are related to the displacement, velocity, and acceleration of particles in SHM, right? Now let's see. So the next topic that we are going to discuss is force law for simple harmonic motion. Please write it down. Please make a note of it. It is force law for simple harmonic motion. Okay. For simple harmonic motion can be written as SHM. Okay. So what does this force law state is? We know that F is equal to m into A, right? So this is according to Newton's second law, right? But when we talk about an object in SHM, the object is experiencing a retarding force as well, which is given by the value kx, which is the formula for the restoring force. Why I'm using the word restoring force is because here we have something called as mean position. So any object which has actually got displaced from its mean position, if it is expected to come back to its position, then there should be a restoring force acting on it. As you know, when you talk about a pendulum, there is a mean position. So as it is away from the mean position, there should be a restoring force acting towards its mean position. Similarly, when you talk about a spring, if a spring has got elongated, it should come back to its mean position. If it is compressed, it has to go back to its mean position. You talk about a swing. Swing and simple pendulum have the same principle, right? So restoring force is needed. Here, the point that we need to keep in mind is we have written F is equal to ma, but an object in SHM is always a function of time, right? So f of t is equal to, can I write m into a of t, where f of t represents force as a function of time. So what I've written here is force as a function of time. I hope it is clear. Fn stands for function, right? So m into, what is the acceleration? Acceleration of an object in SHM is minus omega square x of t, or you can write y of t also. Can I write it like this? So minus m omega square x of t is going to be the force, and let me call this as equation number 1. Similarly, if I take the restoring force as a function of time, the restoring force as a function of time is equal to minus k into x of t. Let this be equation number 2. I wrote the minus sign because it's a restoring force. Negative sign indicates a restoring force. Okay. So what we can say is, comparing 1 and 2, what can I call the value of k as? So if I compare both, I will get k is equal to m omega square. There is an important relation to be noted. Please make a note of this. If there is any doubt, get it clarified.
Sir, can you explain that second step, sir? The ft is equal to MDT below that one. That one I didn't understand, sir. That
F sir?
below the ft is a second line.
This one.
Above, sir. This one, sir. M. That one.
M into omega square. I just opened the bracket. I multiplied. M omega square
No,
into
sir, how
x.
did you get M? That one, sir. How did you come, sir?
How will what become?
How did MA into T become that M into minus omega square x?
Because acceleration of an object in SHM. Acceleration in SHM is minus omega square x. Got it? Acceleration of an object is given by minus omega square. So k is equal to m into omega square.